Okay, folks, so we've taken a little bit of a look inside the chemistry that happens inside these GC columns. Now let's talk about how the columns themselves are made, right? So let's close it out today by talking about the construction of GC columns. And the first thing I should tell you is I've kind of pretty extensively said we're talking about open tubular GC. Packed columns are still technically a thing. It's old school technology. Um, so they're still a thing. It's old school technology, but it's old school technology that still kind of is around today. And if you see one of these things, they're really easy to spot because they just look like a really long LC column coiled up. So it's a stainless steel tube. It's probably something like, so it basically just looks like a long LC column, really long enough to be coiled up into a coil. So 2 to 3 meters of this thing, pretty large inner diameters, several millimeters in diameter. What we really care about, especially for analytical applications, is open tubular, and open tubular columns are almost universally made from something called fused silica capillary. And this is one of those times where I am super bummed that we are not doing class in person because my lab basically runs on fused silica capillary. We have spools and spools and spools of the stuff. Um, and it's a really, really neat material. It's a material I would love to demonstrate for you in person. It's even the kind of thing that occasionally a small piece of it comes home with me in my pocket just because I had it on the desk and I shoved it in my pocket. And so I'd be able to like demonstrate it even here for you on the video, but I checked my whole house. I couldn't find even a little scrap of fused silica, so I'm bummed about that. But I'll describe it for you. You might already be familiar with it, so maybe the miracle of fused silica capillary is already lost on you. Um, but here's what this stuff looks like. It's a glass tube, right? Fused silica is a type of glass that is just pure silica. There's no dopants in it whatsoever. It's also sometimes called fused quartz. Um, and so the way this looks is basically it's a glass tube. So here's a glass tube like this. It generally has pretty thick walls, so that means that the inside of the tube generally has a smaller, so we talk about the inner diameter and the outer diameter, generally a pretty small inner diameter relative to outer diameter. So you get these thick walls. But the beauty of this fused silica material is on the outside, there is a thin coating of a polymer, a polyimide sheath. And the cool thing about the polyimide sheath is that it allows what should be a pretty fragile material, a glass tube, to be flexible to some extent. You can actually take this glass tube and you can bend it and you can wrap it around spools, for example, and the glass won't break, even though that breaking, fracturing is exactly the behavior you would expect from a glass tube. So let's talk about this outer diameters. So that would be this dimension here. Outer diameters are typically on the order of, we'll say, 150 to about 750 microns. So these things are smaller than a millimeter usually in outer diameter. The inner diameter, that's this dimension here, can range anywhere from really small, we'll say 10, all the way up to pretty big, 500 microns. And I'll tell you that we're going to talk about capillary electrophoresis a little bit later in the semester. For GC, we are generally on the higher end of this range. And finally, the polyimide sheath. It usually has a thickness on the order of 10 to 20 microns thick of this polyimide coating. So let's take a look at what that looks like. And I am a little too lazy this evening to cut to a screen capture because I just don't want to do all the editing. So I'm going to do the low-tech version here and just show you on my phone. This is just a Google image search. I don't know if that'll come in focus well enough for you to see. It's a Google image search for fused silica GC column. If we do this, here, let's click on this bad boy right here. What you can see is that basically these glass tubes, you'd expect a glass tube to be clear. This polyimide has kind of a very distinct orange color to it. So fused silica always has this kind of golden orange color to it. But you can see this glass tube is wrapped around a spool there. That's probably about a dozen wraps around that spool. These things can get very, very long. Let's see if we can find an example of this. I mean, even that right there. Oh, here we go. Here's some killer length. So unfortunately, the focus just isn't there, but there are many, many dozens of wrappings around that. And that's how, you remember we said that open tubular columns need to be much longer. That's how you manage to pack a column that is 100 meters in length, a football field length, inside of a benchtop GC instrument, is by being able to wrap them up into these spools, and by having relatively small dimensions to start with, at least in the diameter dimension. Okay, so that's our fused silica material. Um, the the neat thing about this is that that flexibility that allows us to wrap a glass tube around a spool, it really is all about the polyimide sheath. And so if you want to cut this stuff, this is just kind of a neat little side note, something that I would demonstrate for you if I had some on hand. So to cut this, it's actually really simple. All you do is score the sheath. You just score the polyimide. And because this thing requires that polymer sheath to be flexible, the moment that polymer sheath is compromised, you score that polymer just a little bit with like a little scratching tool, and as soon as you try and bend it, it snaps right there at that point. So it's really neat material, and it's a really flexible material to use. Flexible, literally flexible, also very diverse in application to use in the lab. Okay, so where I left you last time was to say that uh, we worry about adsorption in LC onto the stationary phase particles, and that is something that prevents us from doing some of these retention indices in LC that we do in GC. And so let's start addressing this question: why aren't we worried about adsorption in GC? Right? Why aren't we so worried about absorption in GC? And we'll get an idea for this if we look inside one of these these fused silica capillaries, and we look at kind of what the structure would look like of one of these columns. So we're going to cut this thing in half, and we're going to look at the cross section. It'll look something like this. There's a thin polyimide sheath. Right, that's our polyimide. We get some pretty thick layer of fused silica. And then we're going to have a thin layer on the inside wall here of stationary phase. That's our stationary phase. And of course, we'll complete this cross section. We'll say there's stationary phase on all walls here, so that's stationary phase also. There's some fused silica and some polyimide, and our gas flow goes in this direction. Okay, so the stationary phase coating, this stuff right here, let's start a new sheet. Let's see if we can do, there we go, that'll work. So this stationary phase coating is actually, so we're going to call this a stationary phase, yeah, the coating is a thin film of liquid. And that liquid completely covers the underlying surface. So where we talked about bonded phases, and we said maybe we get, you know, a 50% yield, that means half of the surface functional groups are still accessible. In this case, you have a film. The only way to this underlying surface where adsorption can happen is literally through the stationary phase film. So that film thickness is generally on the order of anywhere from 100 nanometers thick to about 10 microns thick. So pretty wide range there. but it's generally a relatively thin film on the walls. And the thing that we should think about this thickness, because it's a factor that we think about when we select a column, is that when we increase thickness, what we're effectively doing is we are increasing the volume of the stationary phase. And that matters. That matters because if we go back to some of our basic chromatography theory, we know that our retention factor lowercase k is the product of our equilibrium coefficient capital K times the volume ratio of the stationary and mobile phases. As you increase stationary phase volume, you increase that volume ratio, you increase lowercase k, right? You increase your retention. So increasing thickness will also increase our retention. It gives us another really neat property too, and that is it will increase our ability to load a lot of sample onto this column, right? It'll increase our sample loading capacity. The amount of sample we can inject onto this thing and still get nice effective chromatography. That's really neat because if we think about concentration limits of detection, the more sample we put onto the column, the more number of molecules we're going to be looking at the same low concentration, right? So this will decrease, and that's a good thing, concentration limits of detection. Okay, so increasing sample loading is one good reason why you might want to really drive up stationary phase volume. I really might want to really work on this end rather than this end of the film thickness. Okay, so this actually brings up a sort of an interesting point of contrast between GC and LC. Because if what we're saying is that these thin liquid films can completely cover the surface and therefore give us limited or no concerns about absorption, why don't we do it in LC, right? And so immobilized liquid stationary phases as opposed to these bonded phases, right? So this is basically a liquid that has been immobilized on the walls of the capillary, not a monolayer that's been bonded like in bonded phase LC. These immobilized liquid stationary phases, they work in GC because the viscosity is so low in gases. Low viscosity means low shear forces. That is, low forces acting on that liquid film as the mobile phase runs past the liquid film. So if we had higher viscosity, like in a liquid, we would essentially wash that liquid film off. This is the same reason why every time the wind blows, it doesn't, empty out a pond or a lake or a puddle, because the shear force of the gas going over the surface of a liquid is not always enough to rinse off that liquid completely. If you think about it, it's probably the same reason why those air dryers in the bathroom are so annoying. You never leave with dry hands, right? It's because gas is not a really effective tool for removing a thin film of liquid off of a solid support. Okay, I want to make sure I'm covering all the bases here. Yeah, so let's finish up by looking at 3 ways to immobilize stationary phase in this manner. So the first one is by far the most common way that this is done. It's the way I drew it in our previous sketch. This is called wall coated open tubular columns, or WCOTs. And if we look, so now what we're going to do is we're going to look down the end of the capillary. So the capillary looks like this. There's a polyimide coating on the outside. There's some fused silica, and just for my artist abilities, let's make that inner diameter nice and big so that I can draw inside of it. So that's looking down the end of the capillary, and what you have is a thin film, exactly as we drew in the previous figure, a thin film of stationary phase that just kind of coats the wall like that, right? So that's the stationary phase material. And it's immobilized directly on the wall of the capillary. So this is our starting point. We're gonna say this is by far the most common. It's the standard If you are starting out, this is where you want to start out. But there are two additional ways that we can get at this, and they are both basically designed at the idea of getting to this higher volume of stationary phase. So the next way is something called, I think I'm gonna have to draw the capillary even bigger this time. It's something we call support coated open tubular columns, or SCOTs. And a support coated open tubular column, if we look down the end of the column, would look something like this. I'm going to draw it really big, so I have a lot of room to draw. There's our inner diameter. I'm not a great artist. What you would find on the wall of this stationary phase, of this capillary, are these support particles, something very similar, few silica particles like you might find in LC. And each of these is coated on the surface with stationary phase material. All right, so the idea here is that stationary phase is coated on a solid support. Solid support, there we go. And then the whole support plus stationary phase, right? The whole particle is immobilized. There we go. My penmanship is just as bad as my artistry tonight. I'm sorry about that. Okay, so a couple reasons why this is good. The first thing is that we are increasing the overall, so this increases the overall volume of the stationary phase. We said that's why we're doing it. It also, if you kind of think about everywhere you have access to here to diffuse into and out of the stationary phase, it also increases the surface area. And that's good. It gives analyte more access to the surface. Here's why this isn't perfect. It's not perfect because you get rough walls, right? You don't have a nice uniform straight wall here, and those rough walls will increase band broadening. Why do they do that? Well, it's kind of like broadening. Here we go. It's kind of like you're adding a very small, not nearly as dramatic as you get from a packed column, but you're adding a small A term, right? Because you have some analytes that are going to run through, we're going into and out of the plane of the board here, but some that are going to run there and some that are going to run there. And there's going to be kind of lateral diffusion over and under, and you're going to be able to get two analytes that run two different paths as they go down into the plane of the paper. So we're basically adding a small A term, which we said we were getting away from when we do open tubular, and that's one of the reasons why open tubular is so awesome. So there is a solution. There's a way to get very large volumes of the stationary phase, but not have this added A term, and it is to use a porous I don't know how to spell, there we go, porous layer open tubular column, or PLOT. Here's how this works. So there's a fused silica capillary. And what you're going to do is you're going to chemically etch, you're going to treat the inside of this capillary to make kind of a porous layer, a spongy layer, right in the vicinity of the inner wall of the capillary. So liquid can get from this volume down into here. So here we go. You're going to etch a porous layer. And then on top of that porous layer, you're going to coat. So there's your porous layer, but you're actually going to put a coating of stationary phase, and that coating of stationary phase is going to permeate deep down into that porous layer. There it is. So stationary phase fills the porous layer, plus we get a surface coating. of stationary phase, and you end up with the same smooth inner wall that you get from surface support, yeah, wall coated stationary phases, but you get all this extra volume into the porous layer of stationary phase. So this allows you to increase uh, the volume of the stationary phase without adding rough walls or adding that extra small A term. I think that's where we're going to leave it off tonight, guys. I will have more for you on Friday. I hope things are going well with the exam. Let me know if you have any questions.